Hello everyone. Welcome to the problem solving season of week 6 of the course Introduction to Rings and Fields. And I am Siddhartha Pramanik. I am a research scholar from the Department of Mathematics, IIT Kharagpur. So, let's recall the main topics of week 6. Then I will start solving some problems based on the topics of week 6. So in week 6, we started with the Gauss lemma, and using this lemma, we have proved that the ring ZX, polynomial ring ZX, is a UFD, right? So, and then we started with some methods which proves how to actually, which gives us tools to show that some polynomials are irreducible or not. So that is so-called Eisenstein's criterion. Okay, so then after that we have defined the characteristic of a ring. Characteristic of a ring, and we have also look at couple of examples, and then we have defined the multiplicative subsets. And using this we have also done the localization, and in the end we have studied the local rings, which is an important concept. So these are the topics of week 6. Okay, so let's start with some problems related to the concept of irreducible or reducible polynomials. Okay, so the first problem is very simple. So prove that for every positive integer n, so for every positive integer n, there exists a polynomial in ZX of degree n which is irreducible. So if you give me a positive integer n, I can give you a irreducible polynomial in ZX which has degree n. So that is what we have to prove. So can you try this? Can you give me some example for this?
X square plus 1.
X square plus 1. But this has degree 2, right? So for this would depends on n. Okay. So for n greater equals to 1, uh, let f nx is x power n plus 2, right? Then this is a polynomial in zx. So I am claiming that it is irreducible polynomial in zx. So can you give some argument why it is irreducible? Okay. So to prove this polynomial is irreducible, so I will use the Eisenstein criterion. So Eisenstein criteria, just recall it. So if you have a polynomial, let's say fx belongs to zx, and if there exists some prime element or prime number p, uh, so prime number p such that uh, p does not divide the leading coefficient of the polynomial, but p divide the all other coefficient, and p square does not divide the constant term, then your polynomial fx will be irreducible in qx. Fx is irreducible in qx. And if the polynomial is primitive, if fx is primitive, then it is irreducible in zx. So primitive polynomial means whose all GCD of all the coefficients is 1. So in our case, this is a primitive polynomial. So we can use the Eisenstein criteria if we can find some prime. So just take the prime p. So take p equals to 2 and use Eisenstein criteria. So here 2 divides the constant term, but 2 does not divide the leading term, and 2 square, which is 4, which does not divide the constant term. So by Eisenstein criteria, it is irreducible over Zx. So this is very simple, but the result is very nice. Okay. So from this thing, actually, we can say something more. So in fact, for every positive integer n, there are infinitely many irreducible polynomials in Zx of degree n. So for each positive integer n, you can find infinitely many irreducible polynomials which has degree n. So can you see why this is the case? Okay, so here we have taken x to the power n plus 2, right? And 2 is a prime number. So in place of 2, we can take 3 also. 3 is also a prime number, right? And we can use the Eisenstein criteria for equals to 3. So for any prime number, we can use the Eisenstein criteria, and there are infinitely many prime numbers. by the Euclid's lemma. So that is the main reason. So there are infinitely many prime numbers. So that is the hint. So using this, you can construct infinitely many irreducible polynomials which has degree n. So you just need to take x to the power n plus p, and you can vary p infinitely many times. So is it okay? Okay. So let's see some more criteria which will help us to decide the some polynomials are irreducible or not. Okay, so let R be a ring and f of x uh, belongs to Rx be a non-constant monic polynomial. So it is non-constant and monic polynomial. So monic polynomial means whose leading coefficient is 1.
1.
Yeah. If there exists an ideal, let's say I of R such that uh, so I is an ideal of R, right? So we can take the quotient ring R mod I, and we can take the polynomial ring over that, and from Rx to R mod I of x we have a natural map, right? So what is the natural map? We can take the polynomial like this, an x power n, and we can map it to a0 bar plus a1 bar x plus so on an bar x power n. So we are just uh, reducing the coefficients by modulo I. So okay, so I is an ideal of R such that the polynomial fx bar in R mod I of x is irreducible. Okay, so then the original polynomial fx is irreducible in R of x. So fx bar means image of fx in R mod I of x. So let me write it here. So we have Rx, then we have the ring homomorphism from Rx to R mod I of x. So this is known as the so-called reduction homomorphism. So here fx goes to fx bar. Okay, so let me read the statement once more. So you have a ring R, we have no conditions on the ring, and you have a polynomial which is non-constant and monic. So if there exists an ideal of R such that the image of the polynomial in R mod Ix is irreducible, okay, then your original polynomial is irreducible. So I hope the statement is clear. So here the non-constant and monic, this part is important. So we will see it later. Okay, so let's prove this. So we will prove this by contradiction. Okay. So suppose fx is not irreducible in Rx. So by definition, uh, fx can be written as product of two non-zero non-unit elements, right? So where gx and hx are non-zero non-unit elements in Rx. So fx is monic polynomial, right? So what can you say about gx and hx? So can you say something about the degree of gx and hx?
Degree of hx and gx would be less than the degree of f of x.
Yeah. So
And
yeah, that's all. And the sum of their degree is degree of fx. So degree of g and degree of h is strictly less than degree of f, and they should be greater than 0, because if one of them is 0, then the other one must be degree of f, so that should not be the case. So okay, so let's write gx and fx clearly. So let gx is equals to summation gi x power I equals to 0 to r, and hx equals to summation hi x power I equals to 0 to s. Okay, so since fx is monic, that will imply gr times hs is 1, right? Because that will give you the leading coefficient of f of x. So this means gr and hs are units, and since gh are non-zero non-units, so degree of g and degree of h are strictly less than degree of f, right? So up to this I think clear. So now if you take the image of fx in this quotient ring, then what you will get? So it is basically uh, gx bar times hx bar, right? Because this is a ring homomorphism. So okay, let me write the whole thing. So it is gx times hx whole bar, and this is equals to gx bar times hx bar. But gx is a a non-zero non-constant non-unit polynomial whose leading coefficient is unit. So what can you say about gx bar and hx bar? So gx bar and hx bar are also non-zero because their leading term is a unit in R. So it will also be a unit in R mod I, right? So they are also non-zero and they are non-unit in R mod I of x. So that implies fx bar is irreducible. Sorry, not irreducible. Is not irreducible in R mod I of x, because we are writing as a product of non-zero non-unit elements. So this is contradiction, because I is an ideal such that fx bar is irreducible in R mod I of x. So what we have assumed is wrong. Hence, fx is irreducible in R of x. So this completes the proof. So is it okay, or do you have some doubt in this?
No doubt, sir.
Okay. So the monicness is important. So let's see some example. So let fx y equals to x square plus xy plus 1 belongs to zxy. Okay, then okay, so that fxy is irreducible, is an irreducible element in the ring zxy. So observe that in the previous theorem we have talked about just polynomial ring in one variable, and this problem is about polynomial ring in two variables, and I want to use the earlier problem. So how to use this? So just think for a few seconds. So the polynomial is x square plus xy plus 1. So we need to prove that it is irreducible in z x comma y. So how to do this? Yeah, any idea? Okay, so first of all, we need a polynomial ring in one variable, right? So here the ring is z x comma y. So we can write this as z y comma x also, because these are variables. So this does not matter. And this is basically z of y of x, right? So here your r is z of y, and you need to find an ideal in z of y. Okay, so take I equals to, so okay, let me be very clear. So here fxy equals to x square plus xy plus 1. So you want to write it as a polynomial in z of y of x, means whose coefficients are in z of y. So how you will write this? So it is already in the form, right? Because here the coefficient is 1, which is in z of y. Here the coefficient is y, which is also in z of y, and 1 is in z of y. This is clear, and this is a monic polynomial. So it, this is a monic uh, polynomial in zxy, and clearly it is non-constant. Okay, so take the ideal I is generated by y. So here you have z of y of x, and you are mapping it to z of y modulo y, then you are attaching x. But what about this quotient ring? This is just z, right? So this is isomorphic to z of x. So here you have f of xy, and you need to take the image here. So how it is look like? So then f of xy bar. So what is f of xy bar? Can you say what is f of xy bar? So we are just going modulo by y. So just kill elements which involves y. So here the only element which involves y is xy. So it will be basically x square plus 1 is in zy modulo y of x, and this is basically z of x. So now you need to check that this polynomial is irreducible in this ring or not. But it is irreducible, right? That we have done earlier. Also, x square plus 1 is irreducible in zx. So that is why our earlier result. So because this is a degree 2 polynomial, right? And it has no root in z. So you cannot factor this polynomial into smaller polynomials. So this has to be irreducible. So by the earlier result, f of xy is irreducible in zxy. So is it okay? So did you got the idea how we have exploit the idea of the previous result? Okay. So in this multivariable case, we can also use the previous theorem. So that is something I want to point out. But in this case, we have to be little bit careful. So the monic polynomial part, that is important. So let's see an example which will show that the monicness is important. So let f of x equals to 3x plus 3 belongs to zx. Then uh, there exists an ideal I of z such that fx bar is irreducible. Irreducible in z mod I of x, but our fx is not irreducible in zx. But fx is not irreducible in zx. So can you see why fx is not irreducible? That part is easy, right? So observe that this polynomial is not monic. Leading coefficient is 3, right? So it says there exists an ideal I such that if you take the image of fx, it will be irreducible in the quotient ring, but our original polynomial is not irreducible. So did you understand the statement? Okay, so observe your fx, it can be written as 3 times x plus 1, and here 3 and x plus 1 both are non-zero non-units. So fx is not irreducible in zx. Okay, now take I equals to the ideal generated by 2, and which is basically 2z. So here you have z of x, and you are taking z mod 2z of x. So then what is your fx bar? So x bar is basically 3x plus 3 bar, right? That is 3 bar x plus 3 bar. But in z mod 2z, 3 bar is same as basically 1 bar. So you can write it as x plus 1 bar. And this is a degree 1 polynomial in this ring z mod 2z of x. This is a PID, right? So fx bar is clearly irreducible in z mod 2z of x, but it is not irreducible in the original ring, the fx. So we cannot use the earlier result in this case, right? Because here fx is not a monic polynomial. So monicness is important. Is it okay? Shall I move on? Okay, so it seems it is fine. So let's see one more example which will help you to convince yourself. Okay, so let f x comma y equals to uh, x plus y plus xy plus 1. This belongs to z x comma y. Then uh, fxy is not irreducible in zxy. Okay, so let me write it as an example, not as another problem. Example of 5. But if I equals to ideal generated by y in z of y, then your f of xy bar is irreducible in z of y modulo y, and after that attach x. So this is the statement. So can you see why fxy is not irreducible? Yes, any idea? So here f of x comma y is basically x plus y plus xy plus 1. This belongs to zxy. So this you can write it as z of y of x. So what is so if you write it as a polynomial in this ring, how it will look like? So it just you can take x common, then it is y plus 1 and again y plus 1. So then it is polynomial in z of y of x, right? And what is the leading coefficient? It is y plus 1. So it is not 1. So it is not monic. So here it is not a monic polynomial. So that is why the earlier result is not working here. And also you can see fxy is just basically x plus 1 times y plus 1. So this is to product of non-zero non-unit elements. So fxy is not irreducible. Not irreducible in zxy. Okay, so up to this part it is very simple. So the second part is, if we take the ideal generated by y and go modulo by y, then the image of fxy is irreducible in the quotient ring. So how to prove this? So now, so what is fxy bar? So we are going modulo y. So just kill the elements which involve y. So fxy bar, so here this term involves y and this term involves y. So this will be 0. So this is basically x plus 1 belongs to z of y modulo y and attaching x. And this is isomorphic to z of x. This is a degree 1 polynomial in z of x. So this is clearly irreducible. So this is clearly irreducible in the ring z of y modulo y of x. So did you got the idea, or
Yes,
do
sir.
you have yeah, go on.
Sir, for irreducible, not irreducible, we have to see whether it is monic or not. Is this the necessary condition?
For monic or not means,
You have written no f of
no,
x
no,
y
no.
is
Yeah, this part I have written for to explain that why we cannot use the earlier result, this result which we have proved.
okay, sir.
Yeah, yeah. Any other thing? Okay. So now using that result, let me prove one more technique which will help us to decide polynomial is irreducible or not. So this is problem number 6. So this is basically known as mod p test in some textbooks. Okay, so let's state it here. So let R be a UFD and fx, uh, let's say fx equals to summation fi x power I equals to 0 to n belongs to Rx, be a polynomial. Okay, here we have no condition on the polynomial. Now, if there exists a prime element P in R such that two conditions should be held. So first one is P should not divide the leading coefficient of F, and the second one is this polynomial fx bar is irreducible in, so this polynomial is irreducible in R mod P of x. Then the polynomial fx is irreducible in your original ring R of x. So in this case, we need a prime element P which does not divide the leading coefficient of f, and the image of the polynomial is irreducible in this polynomial ring. Okay, then your original polynomial will be irreducible in R of x. So here we have no condition on the polynomial like monic or not, but we have condition on the ideal. That ideal should be generated by a prime element. So let's see the proof of this. So I hope the statement is clear. So we will use the same idea in the as in the earlier case. So let's do it by contradiction. So suppose there exists a prime element P belongs to R such that these two conditions hold, such that P does not divide Fn, and Fx bar is irreducible in R mod P of X, but Fx is not irreducible in R of X. Okay, so we are assuming this. So we need some contradiction. Fx bar, sorry, Fx is not irreducible in R of X. So from this we can write, so then f of x equals to some gx times hx, right? This is by definition. So where gx and hx belongs to rx, uh, are non-zero non-unit elements. So p does not divide the leading coefficient of fn, right? So that will imply the fx bar is not a zero polynomial in this ring because its leading coefficient is not zero. So what will happen if we take this image? So since p does not divide fn, that will imply fx bar is non-zero, and that will imply gx bar times hx bar. uh, okay, before that, let us write gx and hx more explicitly to understand it better. So let gx equals to summation gi x power I equals to 0 to r, and your hx is summation, let's say hi x power I equals to 0 to s. Okay, now uh, p does not divide fn, that will imply fx bar is non-zero, so that is clear. And that will also imply p does not divides gr times hs, because this is the leading coefficient of f, because gr times hs is your fn, right? From this, what can you say? So p is a prime element, right? So you need to use that fact. So this will imply p does not divides gr and p does not divides hs, because if p divides at least one of these, then p must divide the product also. So this will imply gx bar and hx bar are non-zero and also non-unit elements in R mod P of X. So that will imply Fx bar equals to Gx bar times Hx bar is not irreducible in R mod P of X. So this is a contradiction. So this is a contradiction. So our claim is wrong. So what we have assumed is wrong. So that means fx must be irreducible in R of x. Hence, fx is irreducible in R of x. So, is the proof clear? Okay, so I hope the proof is clear. So let's see one example how to use this one. So problem number 7. Okay, so take fx as 21 x cube minus 3x square plus 2x plus 9 belongs to zx, and prove that fx is irreducible. Fx is irreducible in zx. So z is a UFD, right? Because it is a PID. So we can use this earlier mod p test. So can you do it yourself? Just think for a few seconds. So you need to find some prime element p in z. Then you have to reduce modulo that p. So just see the conditions for the prime element. P should not divide the leading coefficient of Fn, and the image of Fx should be irreducible in this polynomial ring of the quotient. So what prime number you can take? So prime element in Z means 0 and the prime numbers, right? So what prime number?
Three, two we can take. We can start with two.
Yeah, 2 you can take because 2 does not divide this leading coefficient. So let's try with p equals to 2. So take p equals to 2. So let's check the two conditions one by one. So first one, there is nothing to check. So then p does not divide 21. And what about the second condition? What is fx bar here? So fx bar, you just reduce every coefficient by modulo 2. So uh, you just, if you take mod 2, it will be just x cube. If you take mod 2,
Minus x square
yeah,
plus x plus 1.
plus does, no, it is not x, it will be 0, right? You are going modulo 2
Ah, yes, modulo 2 it is 0. Yes,
plus
yes.
1. So x cube minus x square plus 1. So you need to check it is irreducible in z mod 2z of x or not. So can you say why? Can you check this is irreducible or not? This is very simple, right? Uh, so you are in very special case. Your coefficient ring is z mod 2z. It has only two elements, and this is a polynomial of degree 3. Yeah, do you have some argument here to prove that it is irreducible? So if this polynomial is reducible, then what can you say?
If it is reducible, then we must have three roots or factors.
No, no, no. this is a degree 3 polynomial. If it is reducible, then this is product of some gx times hx, right? So
Yes.
this degree plus this degree has to be 3. So that means one of these polynomials must have degree 1. So that means if this polynomial is reducible, it must have a degree 1 factor. That means if it is reducible, it must have a root. So you need to check it has a root in z mod 2z or not. Okay, let me write all the things. So since x cube minus x square plus 1 belongs to z mod 2zx is a polynomial of degree 3 and z mod 2z is a field. So if uh, x cube minus x square plus 1 is not irreducible in z mod 2z of x, then it must have a root in z mod 2z. Okay, but is there any root of this polynomial in z mod 2z? So z mod 2z has only two elements, right? So for roots you have only two choices. So if you plug in 0, it is 1. So this is not a root.
No root.
Yeah, but here x cube would be 1 bar. X cube minus x square plus 1 bar has no root in z mod 2z. So x cube minus x square plus 1 bar is irreducible in z mod 2z of x. So just use the mod p test. Hence fx is irreducible in zx. So this degree 3 polynomial, in this argument you can use for any field in place of z mod 2z. So that you should remember. That is also one technique. So do you have some doubt in this?
No, sir.
Okay, I hope it is fine for others also. Okay, let's do one more problem regarding this irreducibility. 8. Okay, so let f of x equals to x minus 1 times x minus 2 times x minus 3 times x minus n plus 1 belongs to zx. So this is a polynomial in zx. Okay, then prove that for every positive integer n, the polynomial fx is irreducible in zx. So whatever positive integer you take, this polynomial will remain irreducible in z of x. So this polynomial has very particular form: x minus 1 times x minus 2 times x minus 3 dot dot up to so on x minus 1. sorry, x minus n plus 1. So you need to prove that this is an irreducible polynomial. So think it for few minutes. So one thing I can say is the whatever the earlier methods I have told you, that will not work. Yeah, any idea how to do it? So one general thing I can say is if you cannot find any particular method, so try for contradiction. Okay, so let's see this. So suppose fx is not irreducible. Suppose fx is not irreducible in zx. Okay, so by definition, fx can be written as product of two non-zero non-unit elements. So fx equals to some gx times hx, where gx and hx are non-zero non-unit elements in zx. Some gx hx are gx hx non-zero and non-unit. Okay, so now uh, if you plug into 1 or 2, then what happens? So now f of I equals to uh, okay, let me write the other way. Okay, so g of I times h of I, which is your f of I, this is basically 1, right? For I equals to 1, 2 up to n, right? So this is 1. Okay, this is plus 1 or minus 1. Oh, okay, sorry, this is minus 1. So this is minus 1 take. So this is also minus 1. So from this you can say gi equals to minus hi for I equals to 1, 2 up to n, right? Now that will imply g of I plus h of I equals to 0 for I equals to 1, 2 up to n. Now take a new polynomial, let's say q of x equals to gx plus hx. Then what can you say about the degree of this polynomial? Yeah, anyone? What can you say about degree of qx?
1.
1.
No, it would be 0 because g of I is equal to minus of h of I. So it would be 0
Yeah, 0, but why?
because you have written g of I is equal to minus of hi.
Yeah.
So for this, all the variables will get cancelled if you are writing polynomial. So we left with a constant only if it is there.
No, no, no. G of I plus h of I is 0 for I equals to 1 to up to n. So from that, how you can say that this polynomial is 0? Okay, so just you go back to this equation. So we are in zx, right? So uh, now degree of gx times hx is basically degree of gx plus degree of hx, right? And this is equals to degree of fx. Yeah, am I doing some mistake or? Yeah, so what is degree of qx? It is basically degree of fx. Okay, is n or what? So we need to take x one more. So degree of qx is equals to degree of fx, right? And it is basically n because you have here n terms. But we have n roots. So we cannot conclude it from here. Okay. So do you need some another method or what? Yeah. Do you have some idea? Or can you see it? Can you see it from here? Okay. So it seems we cannot do it from here. We need some another idea. Okay, so let's not waste the time. Let's skip this now. I will come back later. with this.
Okay, sir.
Yeah. Meanwhile, if you have got some idea, you can also share the idea. Okay. So, what the other things we have done is the multiplicative subsets, localization, and local rings. Right. So let's see some problems related to the local rings. So before that, just recall the definition of local ring. So what are the local rings? So a ring R is called a local ring if it has only one maximal ideal. So only one maximal ideal, right? So we have also done one equivalent condition for it. So if R is a ring and I is an ideal of R such that all uh, elements uh, not in I are units, then R is local. That means I consist of non-units. Exactly all the non-units are contained in I. So I is a proper ideal, definitely. So if all the non-units of a ring forms an ideal, then that ideal must be a maximal ideal and it has to be the unique maximal ideal. So I hope you have you can recall it from the lectures. Okay, so let's check a couple of rings which are local or not. So check the following rings are local or not. Okay, so the first one is uh, R of x comma y modulo x square plus 1 comma y. So this is the quotient of the polynomial ring in two variables. Second one is zxy polynomial ring two variable over z modulo x square plus 1 comma y. The third is, let's say, zxy modulo x comma y comma 5, let's say d. It is zx modulo x comma 9. Yeah, let's try with this 4 only. So let's check one by one these are local rings or not. So we just need to check this rings has unique maximal ideal or not. So what about the first one? The first one is easy. Okay, all of these are easy. So can you check the first one? So can you identify this ring with some known ring by using the earlier methods which we have done in the earlier weeks? Okay, so let me do the first one. Then it will be easy for you to do the other problems also. So here you have r, x, y, and you are going modulo this ideal. This ideal has two polynomials, x square plus 1 and y. So you need to go modulo by these two polynomials. So you can first go mod by x square plus 1, or you can go mod by y first. So, so if you go modulo y, what you will get? So what is rxy modulo the ideal generated by y? Can you say what is this? So recall that Rx modulo ideal generated by x is isomorphic to R, right? So this is something which we have done. So using the similar idea, Rxy modulo y, this you can think as Ry mod y attaching x. So these are isomorphic, and this is R of x. So this, if you go modulo y, you will get R of x. Now what is the image of x square plus 1 in this? It remains same, right? So you just need to go mod by x square plus 1. So what is Rx modulo x square plus 1? So this is something well known, and it has been done in the lectures also. So this is basically C. So here what I have done, I have first go mod by y, then I have go mod by x square plus 1. So you can do the other thing also. So you can first go mod by x square plus 1 also. So what will happen in that case? So rxy modulo x square plus 1. So this you can think as rx mod x square plus 1 attaching y. So that will be c of y, right? So let's write it down. So it will be c of y. Now you need to go modulo by y, and cy mod y is basically c. So whatever the way you go, you will get c. So rxy modulo x square plus 1 comma y is isomorphic to c, and c is a field, right? So it has only one idea, and that is the only one proper idea. So it has a unique maximal idea. So it is a field that will imply local ring. So did you understood this? So if you have understood this, try the next second part. So can you say what will be this quotient? Can you identify this with something known by using the similar method?
Is it R?
Is it so? So first you go mod by y. Then what happens? It is just zx mod x square plus 1. So what is zx mod x square plus 1? So zxy by x square plus 1 comma y. So I am going modulo y first. So that will be zx mod x square plus 1. So what is this? So this is actually z of I, Gaussian integers, right? So I have already done this, I think. So you just go back to the earlier videos and check it. And unfortunately, z of I is not a local ring, right? It has it is PID, of course, and it has so many other maximal ideals. So is not a local ring. So I hope it is fine. So what about this third one? Try the third one. So what about z x comma y modulo x comma y comma 5? So can you identify this? You can try the same method.
Z pi it is.
Yeah, so it will be basically z mod 5z, and it is a field. So it will be a local ring. So here you can go modulo by any one of these three in any order. That does not matter. So but you have to do the reduction in a carefully. You need to check the image. I mean, if you look in this case, in this example, I have go modulo by y first. Then we have the quotient ring, right? So we need to check the image of x square plus 1 in the image in this quotient ring. Image of x square plus 1 in the quotient ring. Then we need to go modulo by that element. But here this element remains same. So I just go mod by that element x square plus 1. But in all these cases the same thing happens. So I think it will work out. So the last one, what about D? Zx mod x comma 9.
X9. Z9 it would be.
Yeah, so Z mod 9z. Is it a local ring?
No.
Why? So what are,
We can find more than one maximal ideal in this case.
yeah, is it so? Can you give examples? So how to find maximal or prime ideals of Z mod in Z? Do you know this?
All prime ideals are maximal ideal in this case. So if it is P is prime, then
Yeah, because it's a finite ring, so all prime
yes.
ideals are maximal.
Hmm.
Yeah, so can you find all the prime ideals here?
Uh,
Just use the correspondence theorem. So it is in fact a local ring, and the maximal ideal is, so with the maximal ideal, so how the ideals in this quotient look like? So if you have Z here, okay, let me write it here. So here you have Z and here you have Z mod NZ. So do you know the correspondence between the ideals of these two sets? So here if you have ideals in Z mod NZ, then you have one correspondence with ideals in Z which contains NZ. So if you take an ideal here I, so the image will be I mod NZ. So every ideal has this particular form, I mod NZ, where I is an ideal of Z which contains NZ. So same for the prime ideals and maximal ideals. The correspondence theorem works. So What about the ideals of Z mod 9Z? So which ideals contains 9Z? Can you say? So which ideals of Z contains 9Z?
3Z will contain
Yeah, any other?
other, not possible, I suppose. 3Z will contain.
Yeah, only 3Z and Z. And 3Z is a maximal ideal. So
Yes,
here
true.
the maximal ideal is 3Z mod 9Z. Okay, so in fact, so let me write this as remark. So for a prime number p and for a positive integer n, the ring Z mod p power nz is a local ring with the maximal ideal pz mod p power nz. So this you can verify in the same way. So this is something useful. So you just have to use the correspondence theorem to verify this thing. There is nothing else. So up to this, do you have any doubt?
No, sir.
Okay. So using this, let's do one more. Okay. So this is something computational. So how many units and zero divisors are there in the ring, let's say Z mod 125Z. So you need to count the number of units, means invertible elements, and the zero divisors in this ring Z mod 125Z. This is a finite ring, so these numbers are also finite. So think it for a few seconds how to do it.
ஏய் 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 ஸ்லோவா போ. நாளைக்கு ஃப்ரெஷ்ஷா ஸ்டார்ட் பண்ணுமா? ம். யூனிஃபார்மா எப்படி? யூனிஃபார்மா எப்படி? How many
பசங்க ஆனா ஹாஸ்டல் பசங்க எல்லாம் கிளம்பி வந்துருச்சுங்க காலையில
zero
வண்டி
divisors are there in the ring?
முன்னாடியே போட்டிருந்தாங்கன்னா மெசேஜ்
Yeah,
எடுக்காதுங்களா
do you have some doubt?
Sir, kindly mute that person.
So okay, so if you have doubts, then you can unmute yourself and or you can write in the chat box. So So do you have any idea how to do this? So first of all, so recall one thing which I have done in my earlier problem solving sessions. So in a finite ring, every element is either unit or zero divisor. Okay, so Z mod 125Z, it is a finite ring. So every element is either unit or zero divisor. So if you can find one of these, the number of units or the number of zero divisors, then you can find the other also. So now can you find at least one of the numbers, either the units or the zero divisors? So the fact is, which I have written is Z mod p power nz is a local ring. So this is also a local ring. So observe that Z mod 5qz is a local ring with the maximal ideal uh, 5z mod 5 power q z, right? And for the local ring, the maximal ideal is consist of non-units. So also we know in a local ring the maximal ideal is the set of all non-units. So all the non-units is contained in this set. So all the units are in the complement of this set, right? So what is the cardinality of this set? So the number of units in Z mod 125Z is, so the cardinality of this ring is 125, right? So it is basically 125 minus the cardinality of the number of non-units. So what is the cardinality of this quotient? So how many elements are there in this idea? So this is something you should do. So Z mod 125Z, this is isomorphic to Z 125, right? So the cardinality is 125. And if you go modulo by 5Z modulo 125Z, then it is isomorphic with Z mod 5Z by third isomorphism theorem. So cardinality of this quotient is same as cardinality of Z mod 5Z, which is 5. So cardinality of Z mod 125Z divided by cardinality of 5Z by 125Z is 5, and this is 125. So what should be cardinality of this? This is basically 125 minus 25. So the number of units is 100. Now what is the number of zero divisors? Okay.
25.
Yeah, so the number of zero divisors is 125 minus 100 is 25. So I hope this is fine. So is it okay?
Yes, sir. Sir, can you just scroll up? Yeah.
Yeah, do you have any doubt?
No, sir. Sir, please scroll down. Thank you, sir.
Okay. So let's move on then. So we have done local rings and some problems. So I can do some local rings. Okay, let's do some multiplicative subsets. 10, 11. So this is true or false type. So check the following sets are multiplicative subsets or not. Okay, true or false. So I don't need to write anything. So first one is let R equals to let's say, okay, R be any ring. Let R be any ring and S equals to R minus P for some prime ideal P. Means S is the complement of a prime ideal. So then S is a multiplicative subset of R. So this is true or false. Now B. So let R be any ring and I be an ideal of R. So I be any ideal of R. Then S equals to the set 1 plus I. Okay. So this is basically 1 plus A such that A belongs to I. So then this set S is a multiplicative subset of R. Now C. Okay, let's do this two things. Okay, so try to think these two. Try the first one. So what is a multiplicative set? So if A is subset of R, then S is multiplicative set if it satisfies two conditions, right? So first one is 1 should belongs to S, and second one is if A and B belongs to S, then that should imply the product is also belongs to S. So for this 2S, for each of the two questions, you need to check these two conditions. So try the first one. So first one is true or false? Did you got any answer? Yeah. Any answer? Okay, let's check the first one. So we need to check two conditions, right? First one is 1 belongs to S, and if A comma B belongs to S, that should imply the product is also belongs to S. So that is the definition of multiplicative subset. So in the first one, what is your S? S is the complement of a prime ideal. Now 1 does not belongs to P, right? Because P is a proper ideal. So that means 1 belongs to R minus P, which is S. So the first condition is satisfied. Now so we need to check the second condition. So let A and B belongs to S. So that will imply A and B belongs to R minus P. So that means A and B both are not in P. So that will imply the product is also not in P, because P is a prime ideal, right? Because if the product is in P, then one of A or B must be in P. So this implies the product belongs to R minus P, which is S. So this is a multiplicative subset. So this is true. So is it okay? Okay. So for part B, yeah. So just try the part B in a similar manner. Try to check it.
Sir, is it false because 1 does not belongs to S?
1 does not belongs to S. Is it true?
Because it is written as 1 plus I know.
Yeah. So how does the set looks like? It is 1 plus A, where A belongs to I. So the ideal contains 0, right? So you can take 0. A equals to 0.
Okay, okay.
So 1 is in S. The first condition is satisfied. So here your S is 1 plus I. Now since 0 belongs to I, that will imply 1 plus 0, which is 1, that belongs to 1 plus I. Now what about the second condition? So let 1 plus x and 1 plus y belongs to 1 plus I. So what about the product? 1 plus x times 1 plus y. So this is 1 plus x plus y plus xy. So x, y and x times y, all these is in I. So their sum is also in I. So this should be in I because I is an ideal. So this is also true. So both these sets are multiplicative subsets. So I hope this is not difficult actually. It is follows from the definition. You just need to check the definitions. Okay, so I think it's fine. Okay. So do you have any other doubts?
Sir, are you going to discuss characteristic of a ring in today's class?
Not much because in the lectures I think there was enough examples are there. So do you have
All
any
right, sir.
particular question?
No, no, I'm just asking.
Yeah. Okay. So
So, sir, for local ring, one definition is should have exactly one maximal ideal.
yeah,
And what was uh,
that is something you can take an definition, and the other
and
one you
one
can,
more thing you have stated, no?
yeah, that thing was done in the lectures, right? So if all the non-units of the ring forms an ideal, then also it has to be local ring. Yeah.
And in terms of mapping,
In terms of mapping means what?
one question I saw in the assignment for local ring itself, it was there. I didn't get that one. So
So
after the assignment, we will discuss because tomorrow is the last date. So in the next interaction, I may ask that question.
yeah, yeah, definitely you can ask, no problem. But did you understand that question or not?
No, I did not understand the question.
Oh, so what was that question?
Uh, it is like Z is the ring of integer, Q denotes field of rational number,
Okay.
and recall that a ring R is called local ring if it has exactly one maximal ideal.
Yeah.
And then two options are given here. Let n be a non-negative integer. There exists exactly one ring homomorphism from Z by nz to Z by nz.
So this is not related to local rings, I think. This is,
Uh,
yeah. So I think that definition is given for the other options also. So there might be other,
maybe for it is given for I think third and fourth option there,
yeah,
and
yeah,
these two are independent of that definition.
yeah. This is
Hmm.
something independent.
Okay, okay. I will do that. No issues.
Yeah, okay. So you try the assignments. If you uh, did not get, then we can discuss in the next problem
Yeah,
session.
yeah, sure, sir, sure.
Okay, any other thing or any other issue? So this is the last problem solving season for the ring theory part. But still, if you have any doubt, you can ask in the next season also. but from the next week we'll start with the field theory.
Okay, sir.
Yeah. So if you do not have any other doubts, so let's stop. Okay, then
Okay. Thank you, sir.
yeah, okay.